Unit 2, Lesson 1, Introduction to Functions. So in previous years of math, you've examined a few different relations. So in grade 9, you guys really looked at the equation of a line, which is y equals mx plus b. In grade 10, you guys explored quadratics, which you can write a quadratic in a couple different forms. The first form is factored form. You can also write a quadratic in vertex form. And finally, you can write a quadratic in standard form. And finally, in grade 10, you would have looked at the equation of a circle. So in grade 11, we start to look at functions, okay? And a function is a relation, so it could be one of these, that only gives one unique output for every input. So for example, if you have the value of 2 for x and you plug in 2 into a function, it will only give you one y value or one output. So in the past, you would have looked at certain relations like these two. So this is a linear relation and this is a quadratic relation. And notice that both the relations start with y equal. Now, we are going to expand on this a little bit. So the reason why starting an equation with y equals isn't always ideal is because if I asked you to take this first equation here and plug in 2 for x and solve it, this is what you would do. Okay, you get an answer of y equals 7. Now, the only problem with this type of notation is if you were to look at only the final line, you could only get one piece of information from that last line. You only get the output, right? We plugged in 2 as our input and the resulting output was 7. And that final line only tells you the output. It does not tell you what the original input number was to gain that output. You're going to see why this function notation is better for that. Okay, so function notation replaces the y equals with something like this, f bracket x or g bracket x. And we pronounce that as f at x or g at x. Okay, so from now on we are going to be replacing our y equals with f at x equals or g at x equals. Now the reason why this function notation is so much better, so if we go back to this original example, okay, now I'm going to write it out in function notation. So f at x equals 3x plus 1, and I tell you to do the same thing. I say plug in 2 for x just like we did here and solve. Okay, so I'm going to now go to my function notation. I'm going to replace every single x with a 2. And then I'm going to solve the right-hand side. So f at 2 is equal to 7 after you do the simplification. Okay, and the reason why this is so much better is because now, when you look at that final line, you get 2 pieces of information. Okay, you know that the input was 2, that was the x value that you plugged in. And you now know that the output is 7. Okay, that's the y value. So the last line in function notation gives you a little bit more information than it did before. So example 1, given f at x, which is the equation 3x plus 2, and given g at x, which is a quadratic, x squared plus 2x plus 5, determine the following. So part A, figure out what f at 1 is. So all that means is take the function that is labeled with the f and plug in 1 for x. Okay, so this equation is labeled f, so that's the one I'm going to use, and I'm going to replace the x with 1. And then I'm going to solve it. So f at 1 is 5. So if you were to plug in 1 into this function, your y value would be 5. Okay, try part B. So pause the video and try part B. You're taking the function labeled g and replacing x with 1. Okay, and this is what you should get. G at 1 is 8. Part C is saying take the function labeled f, but replace x with 5 minus 2. Okay, and now we're going to solve this. So I'm going to simplify inside the brackets first. And there's our final answer, okay? Okay, part D. We're going to take the function labeled g, replace x with 2, and then multiply the whole thing by 3. I'm going to take g at x and replace x with 2. And it is important that you write that piece out every single time. I know it gets a little bit tedious to do that, but it is important. Okay, the next two examples show you that you can also plug in variables. So this part E says, what is f at t? So I'm going to take the function f at x and replace the x with a t. And that's all we can do, right? These guys are not like terms. Okay, pause the video and try part F on your own, and then compare your answer to my solution when you're ready. And the final example, part G, incorporates everything. So if you can do this, you are set. Okay, pause the video and try this one on your own. Then when you think you have the final answer, play the video and compare your answer with mine. Okay, so there's your long extended answer. Now another thing you could have done if you notice this shortcut is we already solved for f at t plus 5, okay? And we could have put that right in here off the start. Okay, so that shortcut option is there as well. Okay, we're going to look at a couple graphs, and I want to teach you guys how to determine if these are functions or not. So what you're going to do is you're going to do what's called a vertical line test. So all a vertical line test is you take a ruler, or pretend like you have a ruler in your hand, and move that ruler from the left side of the graph all the way across the right side, okay? And if your vertical line, which is the ruler, touches the line at 2 different points at once, it is not a function, okay? If it only touches the graph in one spot at a time, it is a function. Okay, and that's just building off our definition of a function. Remember, every x value can only have one y value. Every input can only have one output. So for example, if I have my vertical line here at -1, that's the x value, it only has one y value because I'm only touching the graph at one spot. Okay, and that's going to occur every single spot on the graph, so this is a function. Okay, let's test this second one. It's a quadratic. As we move that line from left to right, do we only ever touch the graph in one point, or are there some times where it's touching in 2 spots? Okay, and if you notice, we are only ever touching the graph at one point. So this is also a function for the same reason as before. Okay, our last one is a circle. So if we do the vertical line test here, you're going to see that in most places, we're always touching 2 points on the graph, right? So where I am right now, we're touching the graph here, and we're touching the graph down here. Okay, so that would mean for this x value here, there are 2 possible y values, one above it and one below it. So that's not a function, because functions only have one possible output for every input. Okay, so we know how to determine if a graph is a function. Let's learn how to figure out if a set of ordered pairs is a function. Okay, so we're going to look for the same thing. Does every x value have one y value? Okay, so we just need to see, are there any points that have the same x value? And if there are, do they have different y values? And if they do, that means that that one x value can have 2 different options for y, so that would not be a function. But in this first set of points, we're actually good, right? We have all different x values, which means that every x value in this function has only one output. Okay, let's check out the second one. Does every x value only have one output? Okay, no, look at this. So here's the x value 5, and its output is 10. But over here we have an input of 5 again, and this time it has an output of 4. So that means that the input of 5 has 2 possible outputs, 10 and 4. And that is not a function, because functions can only have one output for any input. Okay, let's check this next part. So we have 3 different points. We have all different x values, so that means that every single x value in this function only has one output. Okay, so now we know how to determine if a graph is a function, if a set of points is a function. Let's look at how to determine if equations represent a function. Okay, so this first one here, f at x equals 3x plus 2. We know right away that that is a linear relation because it is a degree 1 equation. So as a result, every value of x has one value of y only. So this is a function. Okay, here we have a quadratic. And we also know from above that quadratics are functions because for every input they only have one output. Okay, here we have a function with a term that has a square root in it. Okay, and it's really important that you guys notice this because when you take the square root of something, there's always two possible answers. For example, the square root of 4 could be positive 2, right? Because positive 2 times positive 2 is 4. Or it could be negative 2, because negative 2 times negative 2 is also positive 4. Knowing that, you're going to probably be able to tell that this is not a function, because for every input, there's going to be two possible outputs. For example, if I said, solve for h at 4, there's going to be two answers. So the first answer for h at 4 would be if I take the positive version of the square root of 4. So the positive version of the square root of 4 is positive 2. And if I add it to 2, then in this case, h at 4 is equal to 4. But over here, I'll show you what the other answer could be. So if I solve this for h at 4, but this time I take the negative version of the square root of 4, so negative 2. Then over here, h at 4 is equal to 0. Okay, so this is an example where one input, right, 4 was our input, has two possible outputs. So it could be 4 or 0. Okay, so because that happened, this is not a function. Okay, the final thing that we are going to learn today is here in example 5. So consider the following graph of the function f at x. Okay, so this function is displayed as a bunch of points. Okay, that's a function, as long as every x value only has one y value. Okay, so they're asking us to determine what f at 4 is and what f at negative 2 is. Okay, so let's solve for f at 4 first. So what is f at 4? So if 4 is our input, it means it's the x value. They're asking what's the y value that goes with 4? So let's find 4 on our x-axis. It's right here. And let's find the point that's associated with it. Right here. Okay, so what y value is that? It's negative 3. So that means f at 4 is equal to negative 3. Now let's solve for f at negative 2. So let's find negative 2 on the x-axis and figure out what y value goes with it. So here is negative 2 on the x-axis. There's the point that it generates, and that point has an x value of 1. So that means f at 2 is equal to 1.